2024 question number 2. Alright, this is a question that starts off relatively straightforward and then gets pretty hairy later on, but let's have a look. So I've only printed it in black and white. I should have printed it in colour. This crystal here is sort of like, it's white with some blue bits in it, which perhaps is helpful later on in the question. Give the oxidation state of iodine in the iodate ions. The iodate ion is IO3 minus, so IO3 minus. Oxygen's going to be -2. 3 of those is -6, so iodine needs to be +5. If you're not happy with working out oxidation states, it's something you definitely want to spend a lot of time, or a little bit of time, working on, because it's just one easy mark, generally. Now, draw the dot and cross diagram of the iodate ion. Now, you'll probably have some preferred method for drawing dot and cross diagrams or Lewis diagrams. I don't. I just try my luck. So I should probably work out actually if IO3 minus. So each oxygen is 6, which is 18, plus 7, 25. Plus 1 is 26, so I've got 26 electrons to deal with. So I'm just going to give my oxygens a full outer shell. So there we go. I've used 8 times 3, 24, so I've got 2 left over, so my iodine gets a full outer shell. It is a negative ion. So there you go. Now, they will accept that. It's not necessarily the best Lewis structure, but they haven't given you any further information. For example, they might have said, draw the dot and cross diagram where iodine has got an expanded octet. So iodine here doesn't have an expanded octet. So you may be familiar with using formal charges to work out which is the best of several different Lewis structures. So here, this has got a formal charge, -1, -1, -1, and this is +2. Iodine generally won't, oxygen's fine with -1. Iodine isn't going to be happy being +2. So a better diagram is going to be with the 2 double bonds. Okay, and they're not fussy about whether or not you draw electrons or bonds. It's fine either way. Although, if I was going to do this, I would probably include my oxygen electrons as well. The Olympiad guys, they're not really testing you against them. Obviously there's a mark scheme, but really they just want to know, do you understand the chemistry? So as long as your diagram is consistent and makes sense, then generally they will be willing to give it a mark. Then we're asked what the most likely bond angle is. So this is essentially the same as ammonia. So you've got 3 bonding domains, 1 lone pair. So it's based on the tetrahedral, but the angle is going to be slightly smaller because of the repulsion from the lone pair. So it's going to be slightly smaller than 1 in 9.5. Excuse me. And then we have a daily dose of iodine equivalent to 130 milligrams of potassium iodide can prevent the absorption of radioactive isotopes. There's actually some quite interesting sort of like a crossover between physics, chemistry and biology here, the use of iodine to prevent the effects of radioactivity. But anyway, calculate the mass of potassium iodate, which contains the same amount of iodine as 130 milligrams of potassium iodine. Okay, so what we have is, we have potassium iodide and potassium iodate. And I have 130 milligrams of that, and I want to know how much of that contains the same amount of iodine as the 130 milligrams of this. So the best place to start here is probably to work out how much iodine is in here. So in order to do that, I need to know my masses of potassium and my mass of iodine. I still don't have a periodic table, so let me just look those numbers up quickly. This is 39.102 and 126.90. So mass of iodine in here is just going to be 126.9 divided by 39.102 plus 126.9. That's the fraction of iodine multiplied by 130 to give me 99.37 grams. So I've got 99.38 grams, milligrams of iodine in there. So the question is, what mass of this do I need in order to get 99.38 milligrams of iodine? Well, I need to work out the molar mass of this. So the molar mass of this is going to be 39.102 plus 126.9 plus 3 times 16, 48, 214. So this is 214.002 grams per mole. Okay. So the calculation is going to be my fraction of iodine is going to be 126.9 divided by my total 214.002 multiplied by what equals 99.38 milligrams. There might be a better way of doing it. You might have a preferred method, but that's the way that my brain is doing this question. So I'm going to do that. Times 99.38 divided by 126.9 gives me 168. So I get 168 milligrams. So again, just double check I'm not required any specific unit, calculate the mass yet. So 168 milligrams should be fine there. Okay. Iodate ions react with iodide ions under acidic conditions to give iodine. Okay, great. Write an ion equation for the reaction between iodate ions and iodide ions under acidic conditions. So, you're only given one product, which means that we can assume that the iodate ions form iodine and the iodide ions also form iodine under acidic conditions. Now, you should, in order to be able to do this question, there's a method for balancing redox equations under acidic conditions. If you don't know it, what follows might be a little bit tricky to understand, but this is how I would do it. So I'm going to have my iodide ion is becoming iodine, and I balance that, and my iodate ion is also becoming iodine, and I need to balance that as well. Well, I've got one iodine here, two iodines here, so I'm going to put a 2 there. Then I've got my 6 oxygens, so I'm going to add 6 waters to that. I've now got 12 H plus there, and then I need to balance the charge. So this is going to be plus 12 minus 2 is plus 10, so I'm going to add 10 electrons here. Okay, and then I need to just make sure that the number of electrons produced here equals the number of electrons used up here. So I'm going to multiply this whole equation by 5. So 5 times 2 is 10. That's a 5, and that's a 10. And then I can add them together. So if I add them together, the electrons cancel, and I get 10 I minus plus 12 H plus 2iO3 minus becomes 5i2. No. 5 and 1 is 6. 6i2 plus 6H2O. Which is fine. You've got the mark for that. You can go through and divide everything by 2 if you want. So I'm going to get 5i minus plus 6H plus iO3 minus becomes 3i2 plus 3h2o. Okay, so next we are asked, what type of reaction is this? It should very obviously not be a polymerization reaction. Then electrophilic substitution and elimination, Those are organic reaction mechanisms, obviously not those. And then we've got redox and disproportionation. This is the key distractor here. This is not a disproportionation reaction. A disproportionation reaction, you might be thinking, hold on, I go from oxidation state -1 to 0, which is oxidation, and oxidation state +5 to 0, which is reduction. So I've got both oxidation and reduction of the same thing. That's not what disproportionation means. Okay, disproportionation means the opposite. When you start with one oxidation state, and then it gets both oxidized and reduced. All right, here I've got two different oxidation states, and they both end up as the same thing. This is the opposite of disproportionation. This is actually called comproportionation. Make sure I spell it right. Comproportionation, which is the opposite of disproportionation. So just be careful there. The reaction is used to determine the amount of iodate ions in a sample. The sample reacts with excess potassium iodide under acidic conditions, blah, blah, blah. Whereas the mathematical equation reaction between thiosulfate ions and iodine. So this is the same type of thing again. So what we are going to have now is our iodine is reduced to iodide ions, like that. And then our thiosulfate, S2O3 2 minus, and if you've done any sort of redox titration or so like analysis of iron in iron tablets or the Winkler method, you know, the thiosulfate ion comes up all the time because of its ability to react with the iodine, usually with a starch indicator involved somewhere. So that's going to give us S4O6 2 minus. So I'm going to need two of those, which gives me a -4 charge here and -2 here. So that's going to be 2E minus. And then I add them together. The electrons cancel, and I get, write it neatly, I2 plus 2S2O3 2 minus becomes 2I minus plus S4O6 2 minus. Alright, now these two equations here. Let me use a different colour. These two equations, this one and this one, are going to be very important for the rest of the question. So what we've done in this question is we've sort of, the rest of the question is going to rely on our ability to use, or at least the next couple of parts, use these two equations. So it's really important that you are happy with getting those. Personally, I think if you are doing this question during the Olympiad, if you get to this point and you haven't got reliable answers for these two, it's probably not worth carrying on with the rest of the question because you're unlikely to be able to do it. But let's carry on. So next we have the iodate mineral is this, where M is a metal ion and Z is an anion, and the ratio is 1 to 1 to 1. Okay, so I've got M, N plus, we don't know what the charge is on that. We've got IO3 minus, and then we've got Z, we can't use M, P minus, or whatever. All right, but it's 1 to 1 to 1. Okay, and we're told the mass is 255.46, which is easy to gloss over, but will be important later on. And then we are told that 1 gram of this is dissolved in acid. All right, and then the resulting solution was made up to 100 to form a stock solution, from which 10 centimeters cubed is taken. Now, hopefully you'll have done a practical where you've done this kind of dissolve, make up to 100, take 10 centimeters cubed, so there's always going to be a factor of 10 here. And then that reacts with potassium iodide to make iodine, which is then titrated with sodium thiosulfate. All right, so pretty complicated procedure. So what are we doing? In order to find out the amount of IO3 minus, we are first reacting it with potassium iodide. to produce iodine. So we're going to take the potassium, so we're going to take the iodate, all right, in the mineral, and we're going to react it with iodide to make iodine. Now the amount of iodine that I make can be determined by titration with the thiosulfate. Okay, now that would be where you'd use your starch indicator, because the iodine would form a dark coloured complex with the starch indicator, but once it's all been used up it will go colourless. So the amount of iodine that I get from my titration tells me the amount of iodine that's been made from my reaction of the iodate with iodide. Alright, so you might want to spend a little bit of time thinking about that before continuing. And it says now, calculate the volume of sodium thiosulfate solution needed to react with the iodine produced. Alright, so that's interesting, because on first analysis, or on first look, you might be a little bit confused. You might think you might not have enough information to answer this question, because it's asking you how much of the 0.1 molar, how much sodium thiosulfate do I need to react with the iodine? Well, in order to know that, I need to know how much iodine is produced. And in order to know how much iodine is produced, I need to know how much iodate ion I start with. Do I know that? Yes, I do, because I know the mass. And I know that these three are in a 1-to-1 ratio. So 1 mole of this gives me 1 mole of this. Okay, so step 1 is moles of iodate equals moles of MiO3Z, which equals 1 gram divided by 255.46. So that's going to be my moles. 1 divided by 255.46 gives me 3.91 times 10 to the minus 3. Okay, now that is the number of moles. I'm going to write it out. Moles in 100 centimeters cubed. Okay, but I am asked calculate the volume of sodium thiosulfate needed to react with the iodine produced. Well, only 10 centimeters cubed of that was reacted with the potassium iodide. So I'm going to have 3.91 times 10 to the minus 3 moles in 10 centimeters cubed. Okay, so if I've got that many moles of my iodate, I'm going to make 3 times as much iodine. So my moles of iodine is going to be that times 3, which is going to be 1.17 times 10 to the minus 2. No, hold on, let me have a look here. I didn't divide that by 10. That's minus 4. Alright, let's try again. 3.91 10 to the minus 4 times by 3. Okay, so that's 10 to the minus 3. Okay, so if that's our moles of iodine, I need to now know how much thiosulfate is used. So the moles of thiosulfate is just twice that. So the moles of S2O32 minus is going to be twice that, which is going to be 2.35 times 10 to the minus 3. I'm not going to worry too much about my rounding here. The Olympiad doesn't worry too much about rounding unless they like specifically state it, because they're more interested in whether or not you can understand the chemistry. And I think doing a question like this and worrying about both the chemistry and the rounding is a lot to ask, even for this level of work. But anyway, so we now know the moles of my sodium thiosulfate, and I'm asked to work out the volume. Well, I know the concentration, because concentration is 0.1. So if concentration is moles over volume, volume is moles over concentration, then it is 2.35 times 10 to the minus 3 divided by 0.1, which is going to be 2.35 times 10 to the minus 2. Concentration is in decimeters cubed, so that would be decimeters, which is not a great unit to have, but it's basically a litre. So I just times by 1,000, and I should get a reasonable answer, 23.5 centimeters cubed. Again, as always, useful to check, does this make sense? If you're going to do a titration, would you expect to titrate about 23.5 centimeters cubed? Yes. You would not do a titration and titrate like 0.1 centimeter cubed. You can't do a titration like that. Likewise, if it comes out as 7 litres, then that's probably not going to be right either. All right, so it's a pretty involved calculation there. So you might want to spend some time. I've tried to do it as neatly as possible and as logically as possible, but it might require going back through it again. Anyway. Now, however, the metal also reacts with the iodides to form additional iodine. Therefore, the actual volume of sodium thiosulfate solution required in the titration was found to be 27, which is great because 27 is more than my answer. The difference is going to be due to the reaction of the metal rather than the iodate ion. Calculate the number of moles of iodine produced by the reaction of 1 mole of metal ion with excess iodide ions. Okay, so let's just take stock and try and work out what's happening. So we know that I've got this mineral, MiO3Z. And I know that when I react it, the IO3 is reacting with the iodide to make iodine. But now I've been told that the metal is also reacting to make iodine. All right, now this iodine produced here requires 23.5 centimeters cubed of sodium thiosulfate. The actual amount used is 27.4, so the difference between the two is going to be due to the metal. So 27.4 minus 23.5 is 3.9. Okay, so 3.9 centimeters cubed of sodium thiosulfate is required to react with the iodine produced as a result of the iodide reacting with the metal. So we can work out the moles of iodine produced by reaction with the metal. So the moles of iodine is going to be 3.9 divided by 1,000 multiplied by 0.1. It's going to be 3.9 times 10 to the minus 4. And then wait a second, I think I've made a mistake here. So let me just double check. So what I've just worked out was the moles of this. I got a little bit ahead of myself here, so I shouldn't have written that. I should have written the moles of S2O3 2 minus. Because remember, this volume here, that's my volume of S2O3 2 minus. All right, so I use 3.9 centimeters cubed of that, so I have that many moles of S2O3 2 minus. So then I can work out my moles of, if I know my moles of this, I can work out the moles of iodine produced. So the moles of iodine, therefore, is that divided by 2. So I divide that by 2, I get 1.95 times 10 to the minus 4. Okay. So this is the really tricky part of the question. This takes a lot of thinking about. This number of moles of iodine comes from the reaction of the, so that's the number of moles of iodine here that's coming from the reaction of the metal. Okay, thought I wrote down the equation somewhere. Yeah, here. So It's the amount of iodine produced from reaction with the metal. Now the question says, calculate the number of moles of iodine produced by the reaction of 1 mole of metal ion. All right, now let's try and think about this carefully. Well, up here, all the working I've done on this page here is for 1 gram. 1 gram of this. Okay, so, or later on it becomes 10 centimeters cubed. So from this point on here, all these numbers are for 0.1 grams. So from here onwards, it's actually 0.1 grams because I've done the 10 times dilution. So I can see that 0.1 grams of my mineral is 3.91 times 10 to the minus 4 moles. So 0.1 grams of MiO3Z is 3.91 times 10 to the minus 4 moles of Mn plus. Okay, and we've just worked out that that also corresponds to 1.95 times 10 to the minus 4 moles of I2. All right, which is a 2 to 1 ratio. So 1 mole of MiO3Z gives you 0.5 moles of I2. Now, for me, that's pretty difficult. All right, you've got to notice that it's asking you about 1 mole rather than the actual numbers that you were doing with the rest of the question, and then you've got to sort of figure out that ratio as well. So that can take a little bit of work. So if you want, I would probably have a little think about that by yourself. All right, then we are told here the oxidation state of Mn plus in the mineral can be written as plus N. Give the oxidation state of the metal ion after it has reacted with the iodide ions. Okay, so for this we need our ratio that we just worked out. So if I have Mn plus is reacting with I minus to make I2, I've just worked out that 1 mole of this gives me half a mole of that. All right, which means that this and this are reacting in a 1-to-1 ratio. Okay, in other words, I can put a half there. All right, I'm not going to worry about balancing the equation. Because I'm interested in the ratios, but I know that 1 mole of this makes half a mole of that. So here, this iodide is oxidized, so it loses 1 electron, which means that this must gain 1 electron. So the answer is, if it's going to gain 1 electron, it's just going to go down by 1. Okay. When the mineral was dissolved in nitric acid, no effervescence was observed. Give the formula of 2 anions which could not be present in the mineral based on the observation above. So anything that effervesces with reaction with acid is going to be fine. So one that everyone should know is going to be your carbonate ion. So it can't be that, because that would produce carbon dioxide gas. Now the other options are perhaps not as well known, although, you know, if you get that one, you probably should be able to get that one as well. So carbonate and hydrogen carbonate or bicarbonate are going to be both possible answers. There are other answers possible, and the mark scheme actually goes into quite a lot of detail about what you can accept here, but I'm not going to get sidetracked by it. So then the final part of the question is, considering all the information in the problem, choose from the list of ions below which is metal ion M plus and anion Zm minus. So a little bit of detective work. We know that our formula is MiO3Z. We know that IO3 is minus, which means that the charge on the M and the charge on the Z have to add up to +1. So it needs to be something like M2 plus Z minus, or M2 plus Z minus, or M3 plus Z2 minus. So I'm just going to get rid of things that I don't like. Well, copper plus obviously can't work because it's not going to form the next ion down. It's not going to be reduced in the reaction we just thought about. Mg2 plus isn't going to work. That's not a transition metal. It's not going to have multiple oxidation states. Sc3 plus is, can't be reduced any further. Zinc 2 plus probably not. So we're left with these options here. Now at this point it's useful to bear in mind that my molar mass of the ion was given earlier in the question, so 255.46. So I can do 255.46 minus the mass of the iodate ion, which I've probably got written down somewhere. No, I don't have it written down, but it's going to be 126.9 plus 48. So if I work that out, 126.9 plus 48, and I do 255.46 minus that, I get 80.56. So my combination of M and Z has to be 80.56. Alright, which is going to immediately start getting rid of some of these options. So phosphorus with a load of oxygen in it is going to be too heavy. Sulfur with a load of oxygen in it is going to be too heavy. Bromine is going to be too heavy. Hydrogen is probably going to be too light. Okay, so at this point we can just do a little bit of trial and error. I'm going to note the slight blue hint of colour in the crystal picture that we were given at the start, and I'm going to try copper 2 plus to start with. So if I do copper 2 plus is maybe 63.55, so I take 63.55 from that, I get 17, and 17 is my OH minus. Now you can go through and check to see if any of the combinations could work, or you could just stop there. Now 15 marks is not the most marks you're going to get for a question, but it's a lot of marks because that is a difficult question, and as you can see it's taken more than half an hour to go through, and there are some pretty tricky parts, mainly this bit here with the titration. So best of luck.